Hi, I'm Robi, and I'm presenting our work, No-substitution K-means clustering with adversarial order. And this is a joint work with Michal and Moshkovitz. So let's get started. So our general setting is online K-means clustering. As a quick reminder, K-means clustering is this problem where you have a data set X, which is a bunch of points in Euclidean space. And your goal is to find a set of cluster centers, C1 through Ck. The idea being that these will be the centers of the cluster, with all the points X being clustered with the closest cluster center to it. It is called K-means because the loss function takes this form, where we sum the squared distances from each xi to its corresponding center. In the online setting, we're typically presented with X one point at a time, and we need to update our set of centers C on each new point. Oftentimes, this is a constraint so that C always has size K, but that's not going to quite be the case in our setting, which is the no-substitution setting. In the no-substitution setting, we restrict C to be a subset of X, and we have the following restrictions. First of all, every time you add a new point xt, you must either accept it, meaning you put it as a cluster center, or reject it. Don't add it. And all decisions made regarding C are final. So in this setting, we are allowed to remember points or forget them. Like, our memory is a little bit more flexible than it is in many clustering settings. However, the inflexible part is how we submit our answer at the end of the day. Our decisions are final. So the goal is, of course, to minimize loss. And in our case, C has variable size because we're making these decisions about accepting and rejecting. And thus, we want to keep C small, ideally as small as like O of K, or usually we must accept some sort of log n factor, so of K log n, something like that. So I'll be a little bit more precise about our particular problem setting. I'm going to let Lk of X denote the minimum K-means cost of clustering X with K centers. And for any K, I'm going to call an algorithm A an alpha approximation if for any data set with probability at least 90%, it finds a cluster that has approximation factor at most alpha times the optimal. So we're also going to have n, the number of data points, be unknown. So the algorithm sort of has to be ready for the stream of points stopping at any given point. And k will be a parameter provided ahead of time. So our optimization problem formally is for any m, we want to minimize the expected number of centers chosen, expected value of C, subject to our algorithm being an O of 1 approximation algorithm in the no-substitution setting. And in this work, we're going to look at the worst case order on X. This means that we will consider any ordering of a data set X. So the thing about the worst case order is, before going into it, we'll first talk briefly about a few other kinds of assumptions made on X. So the seminal work in this area, Liberty et al., they presented an algorithm with performance approximation factor log n approximation factor. And the center complexity they had was O of K log gamma n log n. And this mysterious gamma term is the aspect ratio, which is essentially the ratio of the distance between the two furthest points in your data set to the distance between the two closest points of your data set. So the implicit assumption their algorithm makes, of course, is that gamma is small. Moshkovitz in 2019 presented an algorithm with approximation factor O of 1 and center complexity O of K log n, considerably better, but the assumption was that the data set had random order, meaning it was a set of points and they were presented in some random permutation. So, of course, what about worst case order, where we don't have either of these assumptions? So the bad news is that the worst case order in general is actually intractable, meaning that there exist data sets where in the worst case order, you are forced to essentially select all the points. So this will be important. So let's go through an example given by Moshkovitz. So fix any constant alpha larger than 1 and consider this data set, which is the set of 1, 2 alpha squared, all the way up to 2 alpha to the n minus 1. And it's a subset of the real line, meaning, of course, we can embed this set in any Euclidean space. So at any time point I, like consider the first I plus 1 points in this data set. And we want to observe that when we're dealing with k greater than or 2 clustering, we can find a 2 clustering, meaning select 2 centers from the set of points, where the total cost is at most 2 alpha to the 2I over alpha. All we have to do is select the point 1, as well as the point 2 alpha to the I. On the other hand, if we don't select the point 2 alpha to the I, and maybe we can even select literally every other point, we see that the cost is approximately 2 alpha to the 2I. Basically, the intuition here is that the last point is very far away compared to the points before it, and therefore it must be given its own center. It follows that any algorithm that does not select 2 alpha to the I will not be an alpha approximation on the first I points of x. And here we're going to use the fact that the algorithm does not know the value of n. So this essentially forces the algorithm to pick 2 alpha to the I for all I. And this is the problem. This basically, formally speaking, Moshkovitz showed that any alpha approximation algorithm must select in expectancy n points, since each point must be selected with probability 0.9. So I mean 0.9 n, which is just omega n. So this is the difficulty. So our job will be to add a little bit of nuance to the worst case analysis. Basically, while this data set is intractable, it turns out that most data sets aren't quite this bad. And in this work, our main contribution is coming up with a way to characterize what makes a data set difficult to cluster in the no substitution setting and what kinds of data sets are more tractable. And we'll kind of have 2 sets of results. One will show a lower bound in terms of our characterization, and 2, to show that our characterization is tight, we will give an upper bound. So let's get on with what our characterization is. So to do so, we'll need a notion of an alpha sequence. I'll first give a disclaimer that for this talk, we're going to focus on the case k equals 2. Details for arbitrary k, of course, can be found in the paper, and they get a little bit more complicated, and the main ideas mostly come out when we consider k equals 2. So a sequence of points is an alpha sequence if it essentially behaves like the previous example, meaning that the distance between each subsequent point to the set of points that came before it, the left-hand side of the equation, is larger than alpha, where alpha is some constant larger than 1, times the diameter of the previous set of points. So this is essentially a set of points that kind of spreads out further and further. And of course, it can be an arbitrary set of points in RD. For any set of points x, we're going to let OC of x denote the length of the largest 2 sequence whose members are distinct elements of x. We just picked the number 2 arbitrarily. The reason for this is because we'll later see that alpha sequence can easily be converted into a beta sequence where alpha and beta are different constants. So in fact, that's the next lemma we're going to look at, meaning that if we have an alpha sequence, we can make a subsequence that is a beta sequence with a minimal conversion factor. We only have to pay a constant factor of log alpha beta. The next lemma is that if we have an alpha or a 1/2 root and alpha sequence, then any alpha approximation algorithm must take 0.99 centers. And this is essentially just a restatement of the earlier bound found by Moshkovitz, just in a more general setting. The point, though, is combining these 2 results, we see that for any data set, there exists an ordering where an alpha approximation online algorithm has to select at least omega OC of x points. Basically, to see this, all you do is you take the OC of x points that consists of that 2 alpha sequence, 2 sequence, then apply the first lemma to find a 1/2 root n alpha sequence and present those points in the beginning. And that is essentially what gives you this lower bound. So, of course, the question now is our lower bound tight? We know that for any data set x, we have to take at least OC of x points, but can we take not too much more than OC of x points? That's the question. So before going into that, however, I just want to circle back to the point we made earlier, which is about not all data sets being bad. It turns out that under pretty mild assumptions, such as x being drawn from a mixture of distributions, however, still being ordered in worst case order, then we can show that with high probability, OC of x is actually polylog n, which is much more manageable, of course, than the omega n shown in Moshkovitz's example. So for our upper bound, we see that OC of x provides a lower bound, and we want to check if it's tight. So the answer is yes, it is tight to some degree. So to motivate our algorithm, we'll look at a special case where k equals 1. And in k equals 1, it just suffices to choose points at random. And basically, for the tth point, we select it with probability 1 over t. And the intuition here is pretty simple. It's just if you select points randomly, you're very likely to select some point that's close to the overall cluster center. Because for k equals 1, we are concerned with approximating a single one clustering of our entire data set. So this gives us a O of 1 approximation with relatively high probability. And the center complexity is log n because of the harmonic sum, of course, summing to log n. So for our general algorithm, we'll kind of do the same thing. So for each point xt, we first have to take this rather expensive step where we compute an offline clustering of the first t points, which we call a comma b. And then we're going to determine the number of points near xt, which is the most recent point we've seen. Basically, if the loss of the points we've seen so far, loss meaning clustering them all in one cluster, is not too much larger than the loss of clustering at two clusters, then we set st, which is the number of points near xt, to be t. Otherwise, we set it to be at, which is the set of the points clustered with xt. And in either case, we will select xt with probability 1 over st. St is sort of here like a proxy for t in the previous algorithm. So it turns out this algorithm suffices. Basically, this algorithm is an O of 1 approximation algorithm. And this algorithm has center complexity OC of x times log n when k equals 2. When k is larger than 2, there's a factor of k also in the center complexity. For the detailed statements of the general results, please consult the paper. There's a few remarks to be made. One of them is that the general algorithm is actually an O of k cubed approximation algorithm, which is quite expensive if k is large. So this algorithm should only be applied for small k. And the algorithm requires memorizing the entire data set. Kind of in this set, in the second bullet over here, we needed to find an approximation offline clustering of the points x1 through xt. So this involves a lot of memory, which is obviously not ideal for most online settings. But this algorithm is not meant for practicality. It's rather meant to show the tightness of OC of x. And we're, improving these things, trying to find a better algorithm, of course, is an avenue for future work. So we believe the main contribution of our work, though, is identifying this parameter OC of x, which allows us to, try to understand worst case ordering for relatively arbitrary data sets. And we believe that our algorithm shows that OC of x is a pretty tight notion of how difficult it is to cluster. So that was all I have today.